Hello and welcome to HW5 Bootcamp. Let's get started. Before we really get started, I want to give credit to this blog from which have stolen a lot of the mathematical equations. Yes, and this is a walkthrough of today's materials. Uh, let's begin with the problem setup. So suppose that I have given you a set of data on the left. I want you to train a model that is capable of generating similar images which are depicted on the right. So ideally, your model should generate something that looks like an apple instead of a banana. Very simple idea, right? So how do we approach this problem? And one of the solutions is called the variational autoencoders, which basically means that in order to generate images that look like the stuff in the training set, you want a model that models the probability density of any given input. And because we are given a training set, we can train our model to maximize the probability of seeing these images in the training set. Right? Make sure you understand this concept. So if we have a model that is able to calculate the probability density of every single input, then we can train it to let it maximize the probability, the joint probability of every data point in a data set. And this is commonly called the likelihood maximization estimation. Um, and in the case of variational autoencoder, besides besides that we are maximizing the likelihood of the training data, we're also assuming that each input is dependent on some unseen variable that we call it the latent variable that follows a certain distribution called the prior distribution. The reason we do this is because there's simply too many possible distributions that we can have if we directly model the distribution of the data of the input. So instead of doing this, we're going to assume that the latent variables are drawn from a relatively easier or known distribution, and then we're going to model the mapping between these two variables, including the posterior distribution, which is the distribution of the latent variable given the observed variable, which is just the variables in the training set, and as well as the distribution of the actual variable given the latent variable, uh, which is the way we can sample a actual variable for the as the generated result of the model given the latent. And the way we do this is by deriving something called an elbow, and we're going to show you right now. The elbow is a lower bound of the log likelihood function. And remember that the likelihood function is the function on the parameters of a distribution given a set of observed data. And our purpose is, of course, to maximize this log likelihood function. And so we can see that this is the definition of the log likelihood function on the joint distribution. So we want to integral along the latent variable to get this partial distribution on the training data, and we multiply the joint distribution with the posterior distribution, and we divide it by the same distribution. This is typo here, I'm sorry. And this effectively becomes the expectation of this term under this distribution. And according to the Genesis inequality, which basically says that if you have a convex function, then the expected value of a distribution inside such that the convex function is smaller than the convex function applied to the expectation of the distribution. Like you can look it up. So, but this basically implies this inequality here, and then you can write this expectation into this integral and decompose this by using the properties of the logarithm function. And this is what we call a variational lower bound because it is a lower bound. And because we want to maximize this function, it is just equivalent to maximizing the lower bound. And yeah. And after we've derived the elbow, we can further decompose the last line by writing it into the expectation format and decomposing this joint distribution according to the Bayesian rule to arrive in this final term. Like these are the detailed derivations. I'm not going to cover them step by step. You can look it up if you want. But at last, we're going to arrive at this equation where the first one is called the reconstruction term, minus the second term, a KL divergence between the posterior distribution and the prior distribution. Like remember that we designed this latent variable to follow some known distribution. This is PZ. And in practice, we are going to assume that the distribution here, which is mapping the distribution of the input data given the latent variable, and the posterior distribution, which indicates the distribution of the latent variable given the input data, to be both Gaussian distributions, because Gaussian distributions have very good properties, and we want to use neural networks to approximate the mean of these distributions for some reason. I'm going to introduce this reason later, but let's just keep this in mind. And an interesting property is that this prior matching term, though it looks very, very, very ugly or very weird, can be solved analytically, which means that we can arrive at like a analytical result instead of trying to approximate using our training data. So what the training process and is to sample the latent variable according to the posterior distribution to approximate this expectation here term here, right? If you think of this. Remember that I say that when we are parameterizing the Gaussian distributions, we're just actually modeling the mean of the distribution. And the reason behind this is that when we're trying to sample the latent variable from this distribution that is modeled by your neural network, and we're trying to update your networks using like backpropagation, because the fact that this variable is drawn from a distribution, we never learn how to pass the gradient through a process of sampling, right? You actually just can't do this. And luckily, we're using Gaussian distributions, which has this nice property, which is called the reparameterization trick. So if you have a variable that follows a Gaussian distribution of this mean and variance, it is equivalent to taking this mean, draw a real Gaussian standard normal variable, and time it by the standard error, so which is this term. And in our case, we're modeling, we're having some parameter here. So the parameter actually goes to these two parts, which is a something plus a ratio of this random stuff that we cannot push the gradient through. And luckily, because these two are deterministic, we can suddenly apply chain rule, not the model parameters. So this is why we are modeling, the mean. So after this is the overall architecture of the VAE. So this is our input. This is our latent. We have this encoder which measures the posterior probability, and we have this decoder that measures the conditional probability. And for VAE, we're modeling these two, but in practice we mostly models this, and we use the reparameterization trick to convert these two into the actual something that is equivalent to drawing a variable from a standard normal distribution with this as mean, this is variance. And when we're updating the gradients, when we arrive here because of the reparameterization trick, we can push the gradients through these, and this forms the training process, right? Okay, so now after we've had some idea about what a VAE is, let's jump to continue to the method of DDPM. So once we've got the VAE, we would like to expand this into a more powerful pipeline. And on the left, it is a simplified model of the VAE where we have the input data and the latent, where we're modeling both the posterior distribution and the partial and the conditional distribution. And on the right, we want to extend this by first assuming that the latent and the input data has the same dimension. We are first changing the posterior distribution into a fixed distribution, which is adding Gaussian noise, which means that for each such posterior distribution, or we call it the forward process, we're using a Gaussian distribution using the previous variable as the mean and some variance. Okay, and we keep doing this multiple times until we get to time t, such that xt after adding multiple Gaussian noises is the same as a random Gaussian noise. And the backward process is this thing we're going to, or the reverse process is this thing, is the partial distribution that we're going to model. And during inference, we're going to generate this data by first sampling from some random Gaussian noise and applying this reverse process multiple times to arrive at the x0, which is the a normal output image. Yes, and another interesting property to note is that under this structure, no matter the if it is the forward process or the reverse process, any variable at current time only depends on the variable at the previous time. So if we just pick a random Q here, a random forward process, say xt plus 1 only depends on xt, right? It doesn't depend on xt minus 1. And it's the same idea for P's, which is the reverse process. So xt minus 1 only depends on xt, not xt plus 1. Keep this in mind. This is going to be important. And there's actually a name for such structures called Markov chains. You can look it up if you want. So this effectively tells us that at each time step, the posterior distribution is equals to this distribution. We can add this x0 freely because it only depends on x only depends on xt minus 1. And we can also decompose this probability using the Bayesian rule, right? It's just that it's the joint divided by the partial distribution. You get the conditional distribution. Yes. Given these properties, let's derive the variational lower bound for this more complicated structure. So this step is where you're going to use the Jensen's inequality, right? Where you have that you write the distribution, the probability into the form of having a joint distribution. You take an integral across the variables. You multiply the posterior on the denominator and outside of the p, and then you move the expectation inside, and you arrive at something like this. Like you can try to you can like use similar steps as the previous slide if you want to verify this. But let's just start from here. You decompose the probabilities using the Markov chain assumption. And after these lines of derivations, I'm not going to go through this line by line because it's too time consuming. You can verify if it is correct. I think it is correct. And at last you arrive at these three terms. First, you get this reconstruction term, which is the expectation under the posterior distribution of the first time step of the log likelihood of the last reverse process. A second is the prior matching term. You got KL divergence between the posterior of the last last stuff in the forward process, which is the pure Gaussian noise. Given your input data, with the actual distribution of the random Gaussian noise. Yeah. And thirdly, you got this denoising matching term where you calculate the expected value of the KL divergence between this particular distribution with the with the reverse process distribution that you are going to model under the distribution of the posterior distribution of xt given x0. So this is very important. Recall that in the forward process, we're saying that we're adding Gaussian noise, which is that we are using the previous term as the mean with some variance. And in this work, the authors assumed for the forward process to follow this particular distribution because they can derive some nice properties. So let's just keep this granted. And also by the recall that we had those reparameterization trick when we use for training the VAE, we can decompose XC into this the mean plus the variance, a standard deviation times a real standard normal noise. Yeah. So by applying this property, this reparameterization trick several times, we can arrive at this final line, which means that at any time xt after the forward process, equals to uh, this alpha bar squared times x0, which is input data, plus square root of 1 minus alpha bar times epsilon, which is a normal noise, a standard Gaussian noise. And well, another interesting property here to note is that if you have two Gaussian variables, the sum of them follows the Gaussian distribution of the mean being added and the variance being squared, added, and taking square root. So this is an important property to make this derivation. Just keep it in mind. You can verify yourself. But finally, we are going to arrive here, and which means that, and we remember the reparameterization trick, we can apply it backwards to get this. So this entire process effectively means that at any time step, the data, the noise data that you're getting after applying the forward process several times, it can be derived one step using this equation. You don't really have to like run through a large chain of t time steps, but rather you can just do this calculation to get the actual xt. Yes, and remember that our objective here, the denoise dimension term, looks like it seems that we can actually solve this analytically, which is a very good news. So let's see how to do it. And to start with, let's use the Bayesian rule. This is just a Bayesian rule, and we have parameterized this particular distribution. And also because of the Markov chain assumption, this is the same as Qx given Qx minus 1, Qxt given Qxt minus 1, which is a normal distribution. And this we have just right now haven't derived this. So this is what distribution that follows. This follows this particular distribution, and this also follows this particular distribution using the same equation we just derived. And after tons of lines of mathematical stuff, we arrive at this equation, which is yet another normal Gaussian distribution with this as mean and this is variance. This is very good news, right? This just means that if we want to minimize this term, well, because this is having a negative sign in front, and the KL divergence is always positive. So in order to maximize the log likelihood, we want to minimize this term. So this means that if we want these two distributions to be as close as possible, let's just let our P zeta, which is the backward process we're going to model, to be following the same distribution as this Q stuff that we have just proved to follow a normal distribution, which means that we are going to parameterize this backward process as following some normal distribution. And again, because of the authors' experiments, they have discovered that modeling the distribution's mean and using the same variance as the Q we derived here is a pretty decent choice. So let's just take this as granted that when we model this reverse process, we actually just models models the mean of the normal distribution with this mean, which is going to be coming out of our model. And this variance the same as what we derive here. Okay. And let's solve this analytically and pretty much similar to what we should be doing for BAE that we did not cover in detail. But after these lines of reasoning, you can arrive at this term, which is some constant times the difference, the L2 distance between the actual mean we derived here and the mean that comes out of our model. So which means that this entire stuff boils down to a sum of the some constant times the L2 distance between the output of our model and the mean you derived. Yes. And recall that we have this nice property where you can get the noise input data at any time step by directly sampling a noise and multiplying it by some constants and the input data, right? So you can rearrange this term, this equation to get this equation, which tells you that you can as a country always approximate the input data at any time given the random noise that is used to generate the current noise data. And we can plug this in back to what we derived for the mean of the Qxt minus 1 given xt and x0. And so after tons of lines of mathematical stuff, we arrive at this final equation. And similarly, like use what we just did, right? If we want the two distributions to be closed, want this term to be closed. And if we want this term to be closed, we can just parameterize this mu theta here as this, like as similar as this as possible. And we know that the only thing that is worse is not fixed is this epsilon here, because the alpha bar is just the product of all the alphas, and the alphas is a predefined value. So what really is variable is the random noise here, right? So instead of measuring this entire mean here, we can just ask it to ask the model to estimate what the only thing that is a variable here, which is the noise. So what we are parameterizing in the model effectively becomes this here. We are modeling the noise and we're converting it into the mean that is our previous variable that is used to derived to be equal to the KL divergence times some constant. Yes. So we plug this in. After some lines of derivation, we arrive at this final value. So this effectively tells us that this entire term boils down to some constant times the altitude divergence between the actual random noise versus the random noise that is modeled by your model. Yes. And this is the end of story for denoising matching term. And for reconstructing term on the prior matching term, like we call this, right? We just noted that this term is equal to some modeling some constant times the altitude distance between the random noise used at time t versus the random noise that your model is trained to predict. And so we're still missing these two terms, the reconstruction term and the prior matching term. So let's step back. And the prior matching term has no parameters. If you want to go back and verify, yeah, let's go back and verify. QXT given x0, we can use our nice property to get it. And PXT, we know that is always random Gaussian noise, right? Because this is the last term of the forward process. So there's no variable here. And if we want to maximize this value by tuning our parameters, we can just forget about this. And for this reconstructing term, the authors have decided to use this particular distribution to adjust for the discrete image space. Just keep this in mind. And remember the elbow, we just discussed that we had a particular expression for this that's very similar actually with what we've derived for denoising matching term. This term has no variables, and this term is a measuring the distance. It's measuring the some constant times the altitude distance between the noise and the noise that your model predicts. So what we only need to maximize is this stuff, because if we have a model that predicts a noise very well, and we plug this back to this equation, we actually minimizes this KL divergence, which in case because there's a negative sign maximizes the entire log likelihood. So yeah, and the authors, based on their experiments, they propose that okay, instead of taking this huge summation here, let's just randomly sample a t from the uppercase t amount of time steps uniformly, and we just calculate the expected value instead of doing this actual sum. And after we've got our simplified training objectives, it boils down to this training process, training algorithm, where we sample a input data, sample a uniformly sampled time step, samples a random noise. We calculate the noise input is our property at times t, and we optimize our model to minimize the altitude distance between the actual noise and the noise predicted by our model. Okay. Now, during our sampling process, well, because we want to arrive at the actual output, so we still have to follow our Markov chain structure to go backward in time. The T subsets, we cannot escape each of them. And at each time, we're going to first start with a random noise because we are assuming that after applying T forward processes, our input data becomes a random noise. So we just sample random noise. We sample each noise to be added at each time step. We let our model predict the noise to be added, and then we use the property to calculate to approximate the input data at each time, and we use this equation here to approximate the distribution of the mean of the previous distribution, and then we use a parameterization trick to get the previous sample. So this is basically the core of DDPM. When you're writing a code, you should basically write training and sampling process with respect to the pseudocode. Okay, and now let's start with DDIM. So a problem with DDPM is this sampling algorithm, where if you see that in the first algorithm, we are training by sampling the time steps, right? But during the sampling process or the inference process, we cannot escape any time step. So let's see how to solve this problem. Let's quickly recap our training objectives. So in this term, T, X0, and epsilon follows our known distributions. T is a uniform distribution, X0 and epsilon are is a Gaussian noise. And so what really matters here is the term inside the epsilon 6 theta, which is the noise predicted by our model. And if this looks a bit unfamiliar, let's go back few slides to this one. So you can see that what our model predicts is the noise, and it predicts the noise based on xt and t. So what is important in the training objective is that we need this so-called marginal term to derive the property for xt given x0. So we can plug this into the xt at any time step. So ideally, if we can design a new distribution that is the forward process, the backward process that is different from our Markov chain structure, but keep this term the same, then we does not modify these training objectives, meaning that we can just take any trained DDPM model here and do the same task. So keeping this in mind, we're going to modify the process from the standard DDPM into this format, where we're directly modeling the posterior distribution or the forward process by modeling this term, right? And in the paper, the authors came up with this particular definition of the distributions, such that this property we just said holds for all t's. There's a proof in the paper that you can check it out. It's kind of complicated, so I'm not going to include it here. But just keep in mind that under this new definition of the forward process, we get to the same marginal distribution of xt given x0. Okay, so given this, and we call this Markov chain here, it can be proved using similar steps as we derived our for DDPM to arrive at this equation. And if we define the reverse process to follow these terms, it can be proved that this particular expression is equivalent to the DDPM of elbow up to a constant, which means that this plus is a constant equals the DDPM objective. And because there's a constant, we don't need to care about this. And maximizing this particular expression is the same as maximizing the elbow for DDPM, which indicates that we really don't need to retrain our model, which is very great. And given this backward process, by this definition, when we're do sampling, we should actually do this, right? Because of the backward process follows a normal distribution. We apply the parameterization trick to get this. And note that this sigma here is a specified value that is not involved in our calculations, not involved anywhere. So ideally, we can set this sigma to be any value, which serves as a scale of the noise. And more importantly, we can set it to be 0. And in this case, if the sigma becomes 0 here, this entire process becomes deterministic. And this gives us two benefits. The first benefit is that if the entire process is deterministic, then given the input noise, I should be able to get a reproducible result as the output. And the second benefit is that by doing some proofs, still is kind of complicated. You can go reference the original paper, but after doing this, we can generate a decent output using less time steps compared to our standard DDPM. Okay, so this is basically the what DDIM does. It takes a trained DDPM model. It redefines the forward process and reverse process so that the objective function remains the same, but speeds up for sampling time. Okay, so now let's enter classifier-free guidance. So problem with our previous model is that we are given a set of data and we're only generating data that looks similar to the given images. And what if I expand the model into instead of giving you a training set, I give you a training set of several classes, and each class contains several images. And I would like to give you a specified class, and the model should generate me a image that looks like the other images in the particular class, which is also set up in the homework. And to do this, we first want to introduce a concept of score. There's another more famous score, which is the stuff used to derive the feature information matrix. That is the gradient of the likelihood function with respect to the model parameters, which is not the one we're going to use here. The stuff we're going to use here is called the Stains score, which is the gradient of the log likelihood with respect to the data. And if the variable follows the normal distribution, we have this formula telling us that the expected value of the mean of the normal distribution given an observed sample equals to the sample plus the variance of the normal distribution times the score. And because in DDPM, we assume we have the property of this marginal distribution of xt to x0 at each time step. We can use the pre-parameterization trick here, plug it into this equation, which is basically like taking this mean, plugging it here to arrive at this equation. So this means that the score in our DDPM pipeline, the score function at each timestamp is basically the noise times a factor. Okay, keep this in mind. And what I mean, so if we want a model that generates conditionally on a class, it means that instead of modeling the distribution directly, we want it to model this distribution of a data conditional to a class label, right? So which means that instead of doing this, we should be modeling this and remember that in this equation we've shown that the score function is equal to the noise times some factor, right? So we can decompose this conditional score by the Bayes' rule into this unconditional score plus an adversarial gradient. And the problem is this adversarial gradient, it is impossible for us to derive this from our model. This unconditional score looks like a vanilla DDPM. So there's a way to solve this. And before doing that, let's assume that we add a factor to the adversarial gradient to control the guidance strengths. And the way we do this is we rearrange the term here to get this term and plug it into our equation here, which has a factor to control the adversarial gradient. And after some derivations, we can arrive at this step where we have a conditional score times the factor and 1 minus the factor times the unconditional score. So this unconditional score looks like what we have for the vanilla DDPM. And this conditional score is something we have to train another model that is conditional on the class label. And in practice, the authors discovered that instead of doing this, let's just create a specific class label referring to no class. and we just randomly we randomly train the model between classless and with class. And if it's classless, the model is trained for this objective. And if it is trained with respect to the class, the model will be trained for this objective. Yeah, so by doing this, we do not need to train a separate model. And remember this relationship we derived between the score and the noise. Since we have this, we can just apply times this vector for each of them and get a similar relationship for the predicted noises. So we arrive at these training functions. See, we create a particular label for classless, and with some probability we train unconditionally corresponding to this term, and for some probability we train conditionally corresponding to this term. And when we're doing sampling, we just follow this term here to tune the gradient toward the class label, and we follow the standard DDPM or like whatever sampling strategy if you want to use DDIM to get the previous mean backward in the time step. Yeah. Finally, we have the idea of latent diffusion models. So for all these previous methods, we're operating on an image space, right? We're converting an image into like a vector and we are doing stuff on them. But nowadays, the image resolutions are actually increasing a lot. A very standard resolution is 224 by 224. We also have 384 by 384. So these are just too large for the calculations we're going to do. And a way to solve this is we map the labels into some latent space, and we operate on latent space using the diffusion pipelines. And after we've generated a latent from a noise, we map it back to the image space by using the sum model we have. And recall the VAE model we introduced at the beginning. What it does is that it maps input to latent and maps the latent back to the input, right? And we can make the latent to have a dimension that is much less than the input dimension. So this arrives at the latent diffusion model where we have this encoder decoder. We map the input data into the latent space. We run the diffusion process and we map it back to the image space. And this saves a lot of time because the latent space can have a very much less dimension than the image space. Okay. And later, Liu is going to lead you guys through a walkthrough of the starter code. And I hope you good luck on the homework.
Hi everyone. We'll walk you through the code for homework 5. First off, make sure you read the write-up and the README to know what you need to do. And for this midterm, you will need to implement DDPM and DDIM. On the README, it will be step 1, 2, 3, and 6, because you would also need to evaluate your model. All right, now let's walk through the basics of this entire repository. In the outer part, you have inference.py, which is used to evaluate your model, in which all you need to do is to basically set up the different classes and then call the evaluate functions from torch metrics. You can read about them in the documentation. For train.py, this is where the main training loop happens. It has like a lot of arguments that you can either pass them in one by one or like set them all in the config file, and basically you'll read all the arguments you need from your config file. All right, and for these different folders, for configs, it is where you would store your configs. We provided you a template for ddpm.yaml. This is like the basic configs that you need. You can add more arguments here as you explore and implement more structures. For models, this is where the modules for our homeworks are. Class embedder.py is used to implement CFG or class-free guidance. UNet modules and unet.py, these two files are the main structure of the neural network using an artificial model. You don't need to like change anything in these two files. And the rest three files are for VAEs. So it is used to implement latent diffusion model. You don't need to change anything in VAE distributions and VAE modules. All you need to do is to basically implement the decode and encode function inside VAE.py once you got to the VAE part, which is technically not required for this midterm report. For pipelines, you need to implement the DDPM pipeline, which is the main pipeline for this entire homework. We'll come back to this later. And for schedulers, you need to implement the two scheduling algorithms for this midterm report. And for utils, we've included some hyperfunctions. In checkpoint.py, we have basically the save, load, checkpoint functions. For dist, we have the functions we need to implement distributed training. For metric, we have a class that's help you to evaluate the model. And for mesh.py, we have functions like setting the random seed and initializing a random tensor, which are helpful in creating random noise for our diffusion model. All right, now let's walk through them one by one, and especially the ones you need for the midterm report. So the first thing you will need to do is to implement DDPM and DDIM. Okay, that's actually all you need to do for the midterm report. Okay, so the first file you will need to change is ddpm.py under pipelines. Here you'll need to implement some some stuff that you need for the midterm report. Now, note that the CFG and VAE, like the latent diffusion model and classifier-free guidance, which are like later parts of the homework, they're all included in this file. So technically, you don't need to like implement these for now, but you will need to do them later. So for sake of time, you can basically ignore the parts where they're not like required for the midterm report. So for instance, if classes is not none, this is the case where we implement CFG. So for the midterm report, classes is going to be none. So you can just basically ignore these for now. But then for the final version, you'll need to like implement everything. So for the midterm report, technically, all you need to do is to use a random tensor to create a random noise as the starting point. And then call self.scheduler, which is initialized in the inner function. This is passed in. And then in the train function, you will need to specify either DDPM scheduler or DDIM scheduler. And then as prompted by the comment, you will need to call set time steps here. And then here is the reverse diffusion process. So guidance scale, this is also for CFG. So technically you can ignore this part for now. And then technically there's nothing you need to do here or here. So here you just need to like pass it through the model or self.unet declared in the inner function. And then technically for the midterm report, you don't need to do anything for VAE. And then you just need to rescale the image here. And that's all you need to do for the midterm report for this file. We'll come back later for the CFG and VAE parts. Okay. And the next thing you will need to do is to change the train.py in the outermost directory. This is going to be the main training function for the entire homework. you will need to create some transformations, load the dataset using the image dataset, image folder, similar from homework 2P2, and add some distributed settings if we need. And then like most things are already implemented for you. Basically, you need to like add the parameters when you initialize these classes. So for instance, here you'll need to like add the different arguments from your config into the declaration of DDPM scheduler. And then similarly for DDIM, you will need to like pass in different parameters here. And then also note that CFG and VAE are like included in this training file, but then they're technically not required for this midterm report. So whenever it is involves like use CFG or like or like use VAE, you can like ignore these parts for the midterm report. And then moving down, we arrive at the main training loop where we basically need to implement a standard training loop. Here you'll need to like set these to training mode, fetch the images and labels from your train loader and send them to the device. This is once you've implemented the VAE, so you can technically ignore this for now. But then once you've implemented VAE, this is like really just calling VAE.encode. I'll show that part later. And then this is for CFG, so you don't need to do it now. But once you've done it, you'll need to like call the class embedder here to process your labels. Then these are some standard code you would need to implement for your diffusion model by calling things like torch.randlike and torch.randin to sample noise and the time step. And then here you will need to call add noise from the scheduler, which we'll see later. And then here we need to like call the UNet, which is our main neural network, for the next time step. And then some standard loss functions and optimizers. And then alas here, if we're using CFG, then we need to like pass them through the pipeline with some different parameters related to CFG, but then otherwise it will be just some standard arguments that needs to be passed into pipeline. And that's it for train.py. And then for the schedulers, this you'll also need to implement both of these for the midterm report. So this is really like the part one homeworks that we've already done. You just need to like follow the formulas and the comments that we've provided for you. You'll need to like read the papers and see what formulas you'll need. I won't go into too much detail here because it's really just like formulating a lot of mathematical equations to see what needs to be calculated. And then similarly for DDIM, just follow the comments and the related formulas. In the paper, we really have already like pointed out which formulas you'll need to reference for you. So just follow the formulas. This is pretty straightforward. Okay. And then to evaluate your model, you also need to add something in the inference.py. You'll need to like basically initialize the different schedulers. And then if you're using VAE or CFG, you'll need to like initialize the class embedder, all that. This is like similar to train.py, where basically all you need to do is to fill in the parameters from the arguments to initialize the different classes you need. And then at last, call these two metrics from torch metrics to compute the FID and IS to evaluate your model. All right, so that's it for the midterm report. And then afterwards, there are two additional steps, like two required additional steps. The first one is to implement a latent diffusion model in which basically you need to add VAE to the diffusion model. And as I mentioned, you don't need to like change anything in VAE distributions.py and VAE modules.py. All you need to do is to basically change the encode and decode functions in VAE.py. And these are like very straightforward. It's really just like 4 lines of code. So just check what is initialized for you and like think about what you need to pass in into encode and decode. It's really just like these 4 components of this class that you need to take a look at and like pass through them. That's it. And then for the CFG, you will need to change class embedder.py. Here you will need to basically use nn.embeddings to like create an embedding layer and to also implement the forward function. Just make sure that no matter for VAE and CFG, once you've like implemented these, you will need to like create a different YAML file and set the flags to true so that let's take a look at train.py. So for instance, you will see that there is args.use CFG. So you need to set this flag to true in either the YAML file, or you need to like pass this as true when you run your train.py. So it will actually run through your CFG or VAE code. And then just remember that once you've implemented these, you need to like change the respective code in train.py and DDPM.py under pipelines of all the related code to VAE and CFG. And then last but not least, we encourage you to like explore other techniques that can help you improve your diffusion model. For instance, for VAE, we would expect you to try VQ-VAE and read the relevant papers and maybe implement them yourselves. And then, yeah, basically that's it. So just a final reminder that the midterm report is due on November 10th. And then for the midterm report, you will need to implement both DDPM and DDIM, which are involving mostly DDPM.py under pipelines, scheduling DDIM.py under schedulers, scheduling-DDPM.py under schedulers, and then the train and inference functions in the outermost directory. And then you can basically ignore everything related for VAEs and CFG just for the sake of this midterm report. So whenever you see something like if args.use CFG or like if VAE is not none, you can basically ignore all the to-dos under these conditions for now. Yeah, that's basically it.